Text feels natural to humans. We read it, write it, and think in it. But for computers, text is not language. It is data that must be encoded. Textual encoding is the process of representing written characters as numeric values so they can be stored, transmitted, and processed by digital systems. At its core, textual encoding maps characters to numbers. When you type a letter, a symbol, or even an emoji, the computer does not store the shape you see on the screen. It stores a numeric code that represents that character. One of the earliest and simplest systems for this is ASCII. In ASCII, each character is assigned a number. The letter A is 65. The letter A is 97. Digits, punctuation, and control characters all have defined numeric values. ASCII works well for basic English text, but it has limits. It cannot represent characters from most languages, nor can it handle many symbols used today. To solve this, Unicode was introduced. Unicode is a universal character set designed to represent text from nearly every writing system in the world. Instead of focusing on a single language, it assigns a unique number, called a code point, to each character. But Unicode alone is not enough. Those code points still need to be stored as bytes. This is where encodings like UTF-8, UTF-16, and UTF-32 come in. UTF-8 is the most widely used textual encoding on the web. It represents characters using 1 to 4 bytes, allowing it to be efficient for common characters while still supporting the full Unicode range. Textual encoding choices matter more than they seem. If systems use different encodings without agreement, text can become corrupted. Characters may appear as question marks, strange symbols, or unreadable sequences. This is known as encoding mismatch. Textual encoding also affects data size, performance, and compatibility. A file encoded in UTF-8 may be smaller than the same text encoded in UTF-16. Some systems expect specific encodings and may fail if the input does not match. Beyond storage, textual encoding impacts data processing. Sorting text, comparing strings, searching for patterns, all of these depend on consistent encoding rules. Even something as simple as uppercase and lowercase comparisons relies on well-defined character mappings. Text is one of the most common forms of data, but it is also one of the easiest to misunderstand. Without proper textual encoding, data pipelines break, integrations fail, and meaning is lost. So whenever you work with text data, remember, text is not just text. It is a structured numeric representation, governed by encoding standards, carrying meaning through agreement. And understanding that encoding is essential to working with data reliably at scale.